Welcome to day 5 and congratulations to make it to the final day. So today we are going to talk about evaluating how good a model is. Let me share my screen to start with. All right, so we're going to have 2 sessions today. So the first session is going to be about what I call basic training and test accuracy. And in a minute, we go and talk about what I mean by this. And in the second session, we are going to learn about the more advanced way of evaluating forecast accuracy, which is called time series cross-validation. And this is basically the most reliable way to evaluate accuracy. So these are 2 sessions that we are covering today. So in the first session, we first understand what we mean by evaluating forecast accuracy and what we do and how R is doing it. And within that, we talk about evaluating both point forecast accuracy and evaluating distributional forecast accuracy, including prediction intervals, quantile, and the whole distribution. So what evaluation of forecast accuracy means, where so far we have learned um, different models. We learn how to specify a model, how to train a model on data, and how use it to produce forecasts for each step ahead into the future. But we haven't really discussed about how good these models are. So when it comes to the question of how good is a model, there are 2 aspects that we need to look at. One aspect is about having a good fit, meaning we have a model that can capture the systematic information that is available in the data. So that is one aspect. And the second aspect is about how good actually that model is in forecasting the future. So I'm going to focus on the second one because that is most important, because our objective is to build models that help us to forecast the future. And I will come back to the first one a bit later, but this is something we have started also discussing when we discuss about white noise process and look at the ACF plus to see if the data is white noise or not. So basically we look at the residuals, which is the difference between fit and actual observations, and we look at it and we check it against certain assumptions, and that tells us whether the model captures the information or not. But let's now focus on the second one, which is about evaluating the accuracy of the model when it comes to forecasting the future. So how we evaluate forecast accuracy? Well, we have to calculate the errors based on a test set. And the test set for us means a period of the data that we haven't used in the training or the fitting of the model. I will show you a graphic, but also a short demo with some drawing, hopefully can help to understand what we mean by this here. So we first calculated the errors, the difference between the actuals and the forecast that we created for the future. And then somehow we summarize these errors to calculate some scores that help us to compare different forecasting methods. So that is one aspect of forecast accuracy. However, there are actually different aspects of what a good forecast could look like. And this is what I refer to as the quality of the forecast. So accuracy is just one aspect of it. But there are some other aspects. The most important one probably is what we call the utility of a forecast, or the business impact or the decision impact of the forecast. Sorry, I think this was an update of the software. So that is the most important one. So again, it goes back to the introduction section where we discuss what we want to do with this forecast, which decisions we are going to make with this. Is it about um, inventory management? Is it about procurement? What is the exact decision that we are making? And can we link our forecast to the decisions and then evaluate the accuracy um, of the forecast first, and then go and also evaluate the utility of it? So when it comes to utility, there are many things depending on the context that you're looking at. Maybe you are interested in scheduling the staff or calculating the emission, or you have a service level, or you want to minimize your stock out or the cost of inventory, or you want to have a fast response. For instance, in ambulance services, this is what we are interested in, and so on. So there is always a business context and a decision that relies on the forecast, and typically multiple type of forecast as well. So it's not just one variable, because the decision-making process takes always multiple inputs. Some of them, they are in the form of a forecast. Now, we can do that, but this requires like building optimization and simulation models, and sometimes might not be straightforward and easy. So that is why when we do forecasting, we start by looking at the accuracy of the forecast itself. But our ideal goal should be go and evaluate the utility. So if you can, you should certainly do that. All right, now let's focus on then evaluating the forecast accuracy. So now before I show you maybe in a graphic and draw something to help you understand this, let's distinguish between two definitions: in sample and out of sample, or training and test. So remember when we use Fable for specify and estimating models using the model table, basically we fit a model on our data, and then we use the forecast function to generate. So when we fit a model, the model generates fitted values, and then following that, the residuals as well. So we have already access to residuals. Now, as I said, we can actually use that to say how good the model is. But just relying on residual is not a reliable indication of forecast accuracy. So having a good fit that describes the data well doesn't guarantee getting an accurate forecast. And this is because we may have overfitting. And then, so overfitting is a very important concept in general in forecasting and machine learning. And in our case, it simply means when we overfit, we try to follow irreducible error or randomness in the data. But remember, we cannot forecast that. So if we do that, we are overfitting. And if we actually try that model on the real data to forecast the future, it is very likely that the forecast wouldn't be good. This is also a very well-known a discussion around two concepts called bias and variance. So it's a balance between bias and variance, and I will later share a link to a chapter of our book where we discuss this a little bit if you want to know more about this. So when it comes to forecasting, our idea is to make sure we capture systematic information, not following noise or randomness. That's one important thing. But at the same time, we don't want to overfit. But if you also fail to capture the systematic information is not good. So overfitting is bad, but failing to capture systematic information is bad as well. So we fit our data in training or in sample, and then we evaluate the accuracy in out of sample or test. And this is a way to see how good the forecast is, not just relying on the fitting, but also in in the real world out of sample, I would say. So to evaluate this, we somehow mimic what's happening in real life situation. So maybe to go actually talk about this, I will share my screen to draw something here. Just sorry, put my chat here in case. All right. Okay, so now let's understand what we actually be talking about here. Sorry, because I cannot see my own screen now. Can I check if you see this whiteboard?
I don't yet see a whiteboard, Bahman.
Thank you. All right, so now let's again go back to some examples we
Bahman,
had.
I don't see it.
Oh, okay. Sorry, this is a bit. Do you see it now?
Yes, I see that now.
All right, thank you. So basically now we have an example that we had also in the past. So I'm just drawing some numbers basically here. So I have the data for the past from the first observation to like last observation. So these are just different values. I'm assuming I'm making a time plot. And then here I have different periods, okay? So I come from the last observation up to the first observation here, and then I'll link all these points, let's say, and then I get a time plot like this. So this is my past. And then this is now, and the rest is my future. So I will show you another example, but let's assume this is a monthly data. And this period T is October 2025. So, and if I measure, let's say, the number of vaccine administrated in Ethiopia, for instance, in the total country, so that would be basically that number. So in y-axis, I have vaccines administrated, and then here I have months. So I have October 2025, and the number that corresponds to that and then September 2025, and it goes back to all the historical those administrated that I have recorded over time. Now I have to forecast what I need for November 2025, January, December 2025, January 2026, February 2026, and for any horizon that I want. All right, so that is the idea. Now what happens is we start with choosing, let's say, one model, but we repeat this for every single model that we use. And what we do is we start by fitting a model, so specify the model in Fable and then fitting it. And then we get the fitted values. So for each observation in the past, I get a fitted value. So I'll just use maybe a green button to make it more clear. All right, so for each one, I get an observation, and then its fitted value. And if, again, I link them together, maybe use this line. So now this creates a fitted value for me, for the method that I'm using. And now the difference, the sort of vertical difference between each 2 points gives me what we call the residual. All right, so we have the actual observations in the past, we have the fitted values, which is the green line, and the difference between each point then we calculate. Like this two, for instance, the vertical difference between these two, the vertical difference between these two, the vertical difference between these two, and so on. So it will give me a residual. Now I can actually go and analyze this residual and see whether it captures information. But remember, I said if we just rely on the residual and how good this green line fit is, we may overfit We don't realize that, but we overfit. And when we use this model to forecast the future, the forecast would be really bad and not helpful, not accurate in this case. So I just wanted to introduce this terminologies that we have residuals here. All right, so the next thing we do is we pass the fitted model to the forecast function, and we forecast for, just to make it simpler, to forecast only for 3 months. So again, going back to the example of vaccine, if I want to forecast for November 2025, followed by December, and then followed by January, these are maybe 3 point forecasts that I generate. But remember, I could also generate a prediction interval if I want, the upper bound and lower bound, upper bound and lower bound, upper bound and lower bound. I could even have the whole distribution, because we can now generate the whole distribution, either following like a normal distribution, or using bootstrapping. Okay. Now my question is, if I want to tell my manager or a donor, for example, in this case, how accurate the forecast is, or am I using the right model to evaluate the forecast, to generate the forecast, then how should I evaluate this forecast? Remember, we have data up to October. I generated the forecast for November, December, and January 2026. So how should I evaluate the forecast accuracy here? And now I have to introduce another terminology that we call it the forecast error. Okay? So there is a difference then between residuals and forecast error. When we refer to the error, forecast error, we're again talking about the same thing, a difference between the actual observation and the forecast that we generated. A residual was the difference between an actual observation and a fitted value. Well, fitted value in a way is also a forecast, but it is just a one step ahead forecast. So here we have 3 step ahead forecast. So we need then to distinguish between a forecast error and residuals. So forecast errors is always calculated based on a test set. A test set is a set of data that has not been used in fitting the model. Remember here, I use all this data to fit my model, and I generate the forecast for here, and I'm evaluating based on that. So the model that I use to fit on the data hasn't seen any data here. That's what we mean by a test set. So, and the difference between the actual observation and the forecast we generate in the test set is called a forecast error. Now, going back to my question, how would you evaluate this? How you calculate the forecast accuracy in this scenario? Maybe you can put your thoughts on the chat. Or if you want to maybe speak, feel free to unmute yourself. Yeah, okay, I agree with you. And also we have to compare the forecast with some test values. But I am here now in October, and I have generated forecast for November, December, and then January. So what should I do now to tell people that this forecast I generated were good or were not good? Well, the forecast error is simply the difference between the actual and then the forecast that you generate for that period. Okay, so let me tell you what we can do here. So, well, to tell my manager or the donors how good these forecasts are, well, I have to wait until the end of November, and then by the end of November, I will know the actual that I had for November. And then I put it here. I have to wait another month by the end of December, and by the end of December, I know maybe this was the actual. And then I have to wait until end of January, and I calculate the actual. This would be the actual. And then if I have more step ahead, I will do the same. I have to wait until end of February, end of March, April, and so on. So what is the problem with this? So now I can calculate this difference. All right, so I can go and say, if let's say just focus on point forecast, so I calculate the difference between these 2 points, and then that's my error. And somehow I can summarize these errors and get a score for it. So can you tell me what would be the problem with this? Is this acceptable in your opinion? Or is it the most clever way to tell people how good my model is? Yeah, so thanks, Amal. I think I don't know whether others agree with Amal, but that's what I want to hear, because I cannot wait actually 3 months, or in some cases, if I forecast for 6 months ahead or 12 months ahead, I cannot 12 months to tell people if my forecasts are reliable or not, because they have to make decision now. All right, so they have to make a decision now about how much to buy, about the level of inventory basically that I need to replenish in this case. So it is just not a good idea to wait for this, because people need to make a decision now. They rely on what I tell them now. So I have to find another way to do this. So if I cannot wait because it's not logical and I have to make decision now, so I have to tell people now if my forecast is reliable or not. So what is the alternative? What should I do now? So what would you suggest in this case to do? Yeah, so that's a very good start. So we have to work with what we have got so far. Okay, what we have got so far is this. All right, all this data from the beginning to period T. So this is all that we got. It's a very good start. But what we have to do with this? Can you think about this? And assuming my forecast horizon here, so my forecast horizon, or just simply I put H because you know what H is. So my H is equal 3 in this case, which is 3 months, because I forecast for 3 months. So what would you suggest to do? Maybe I will wait a little bit more in case you can guess What would be an alternative to this? We can compare the forecast value with the fitted value. We can do that, but this is, again, is residual, so is not a forecast error. Yeah, absolutely. Thank you, Nwoko. That's actually the answer I'm looking for. And again, that builds up on what you said at the beginning, that we work with what we have now. Okay, so let's start with that. We have to work with what we have now. So what I have to do here, given that my forecast horizon is 3 months, what I do is this. I come to the end of my data, the last period in my time series, and then I split my data into two parts. So I would leave out 1, 2, and 3. Okay, I will leave out these 3 periods, and I assume I don't know this. Okay, so I pretend that I don't know it. So what I do then, I will go now, I use this data only to fit my model and the data, and then I will come and produce the forecast. In this case, again, my forecast could be different things. Once I produce the forecast, I come and I reveal the actual observation this time. And then I can now calculate the difference between these errors. And I will show you how we do it for prediction interval, quantiles, and distribution as well. So now I have an error for this period, error for period t minus 2, error for period t minus 1, and then error for period t. Okay, and this is now what we call an out of sample. So out of sample, or out of sample or test, and then the rest we call it, the rest of this here we call it train or in sample. Okay, train or in sample. I think the key here is to remember, when we refer to test set or out of sample, we mean we haven't used that data in the training of the model. All right. So just to repeat very quickly, when we want to evaluate the forecast accuracy of a model based on what we get so far, and then I would say in an ideal situation, I have the data up to now, whatever now could define. So once we have that, depending on what is my forecast horizon, I go to the end of my data, and then I leave out the number of periods that equals my forecast horizon. So in this case, my forecast horizon is 3, so I leave out 1 period, 2 period, and then the second period. And I put this inside a test set variable. I pretend I don't know these values. And then I call the rest train or in sample. And then now I go and I specify a model, and I pass this basically this data to my model function, and I can fit onto this. So I get the residual for it, and then I generate the forecast for these 3 periods. Once I generated the forecast, I can now reveal this actual observations. So what matters here is I pretend I don't know this, even if, I have the data, but I don't use them in the training. So I pretend I don't know. And what actually matters for the evaluating forecast accuracy is this. and then somehow I'm mimicking the real world situation. I assume I don't know this, and my model will be tested on a data that I don't know. I mean, the model doesn't know. So if unfortunately an event affected test value. So if you mean, let's say, if something uh, extremely big happens here, I'm not sure if that's what you mean. So if, like, let's say, I don't know, there was a flooding, or or there was a conflict or whatever, and then that affects either the consumption to be very high or very low. Well, that is the part of reality, and then hopefully the models that you build can account for such things. But and I will discuss also another, and that's what I will discuss in an advanced part of it. So how we can make sure that um, when we come to evaluation, we do something that is reliable, and with confidence, I can actually tell that the forecast model that I'm proposing is a good model. So I'll talk about that a little bit as well. Okay, so far my idea is just to explain what we do and how we evaluate things, but we haven't actually discussed once I get the errors, both for the point forecast but also for the forecast distribution, what are the measures that we use to compare across different models to tell us which model is the best model for us. So let me now go back to my slides to briefly go through this different measures. So this is what I meant when I say we mimic the real life situation. So when I try to forecast the next 3 months, and I am in October 2025, and I have to forecast for November, December, and January, I don't know those three values. And then because I cannot wait, now I say, okay, how can I mimic this real life situation? So I come back and say, well, let's pretend I don't know the last 3 months of my data. I treat them as the future values. So that for the model, this would be new data. So we don't use them in the training. And that's what we call a test set or the out of sample. So the forecast accuracy must be always calculated based on the test set data. And the test set data is a new data to the model. The model hasn't been trained on it. That's what we mean by new here. So that's what I did so far. So I have the whole historical data. I split them into train and the test. So what is the size of the test set? In this case, it equals to the forecast horizon. So how many periods I want to forecast into the future. That determines how many periods I will put in my test set. All right, now let's talk about how we calculate the forecast accuracy using error metrics. Well, we start with calculating the error itself, and the error is the difference between the actual observation and what we forecast. So here we talk about the point forecast for now. All right, so for each period that we forecast, once we know the actual observation, we simply calculate the difference between them, and this will give me an error for each period. So in the example I provided, I had 3 errors. And then following that, I can go through the error metrics and tell you how we evaluate it. So this is an example of the beer production again. So this is something you have seen in the past. So I have my data, I filter just a part of it, and I pass it to model table with 2 models, one seasonal life and another one with mean, and this will give me the model table. I pass the model table to my forecast function. I generate the forecast for 3 years. This is quarterly, so it means my H is actually 12. I have 12 periods in this case. So if I do this, it would be something like that. So sometimes you can visualize your forecast against the actual. So actual is the black line here, and then you have two forecasts. One is mean, and another one is a seasonal naive in the blue line, and the mean in orange. So you can visually see how good the forecast is. And this is also something I showed you how to do it um, yesterday and actually the day before as well, when we visualize the whole distribution and the point forecast, and we put also the actuals. So that gives you an idea of how actual observation is close or far from what I forecasted. So you can also do that visually if you like. But it's better to rely on maybe some numerical error metrics that makes it easy to tell you which method has the lowest error. And by the way, when we talk about error, we always interested in the method that gives us the lowest error, which is completely logical. Now, how we measure the forecast accuracy using error metrics. So there are many, many different error metrics. So here we just talk about a couple of them. So once I calculate my error, and this I have this error for different periods, error for period 1, 2, 3, any number of horizon h that I have. So once I have that, I can use that collection of errors and somehow summarize them to get what we call then a score, a single number that help us to compare across different methods. So the first thing I do is I calculate the absolute value of the error and I take the average of that. If I do that, then I can calculate and score that we call it mean absolute error. So this is one measure of evaluating point forecast accuracy. I can also take the errors, square them first, and then take the mean or average of it. And this is mean square error. And if I take a square root of that mean square error, I get another measure that calls root mean square error. So these are the measures that we call them scale dependent. So the accuracy or the error that we report depends on the scale of the time series. But sometimes, especially if you deal with many time series, you need to work with scale independent accuracy measures. So they do not depend on the scale of the time series. So you can use it for many and compare across many as well. So one accuracy measure that has been developed historically for this is called mean absolute percentage error. So in this case, we calculate the error and then the absolute value of the error, and we divide it by the actual observation. We calculate the average and we multiply this by 100%, by 100, and this will give us a percentage. So sometimes people like this measure because it is in percentage and we can understand the percentage better than an absolute number. Like if we say the forecast accuracy is 5% wrong, I mean, you may have an idea, okay, is 5% in this level, 10% in another level, or in this health facility, the forecast accuracy is 5% wrong and another one is 20% wrong. So sometimes people like that sort of thing, so that's why they use it. But there are some issues with this measure in particular. For example, if you have a low volume time series data, or sometimes the observation close to zero, then you will get big errors for that, which is not what we want, because it's not really telling you what is happening. It is just because the number is small, the error becomes big. But also, if you get zero values in your time series data, then you cannot even use this. So there are some other issues like mean absolute percentage error penalizes overestimation and underestimation with a different weighting system. So you need just to think about it. So, but if you are having, just one time series, you can always use mean absolute error or mean or root mean square error. So these are like good accuracy measures. Now, to overcome the challenge of mean absolute error, so some researchers, including Professor Heinemann, they propose some other accuracy measures like mean absolute scale error. So here we do something similar to mean absolute error, but we scale it and scale it against in sample fitting values that we generate using naive or seasonal naive, depending on whether your time series has seasonality or not. So MACE, mean absolute scale error, is another error measure that you can use. But we have also root mean square scale error. So remember I said MACE is similar to mean absolute error, but scaled. So this one is similar to root mean square error, but scaled. So in this case, you can actually use this MACE or RMSSE for scale independent comparison. So if you have many time series or if you have time series in different scales, so you can rely on this accuracy measures. But there are many other accuracy measures in the literature. So if you want to know more about this, either go to the book or you can also share more resources about this. So sometimes you may want to know what is the best accuracy measure. Well, there is no best accuracy measure really. All entirely depends on what you want to do with that forecast. But most of the time, relying on if you have one single time series, using RMSE or MAE is doing a job for you, because RMSE minimizing the mean of a distribution and mean absolute error minimizing the median. So they give you an indication of the center of those distributions if you use normal in this case. And if you have many time series with different scales, then you can use RMSSE or MACE for that. But there are some other accuracy error measures. We call them relative error measures. Sometimes I use them as well, but this is something you can also develop it yourself. So relative in this case means, let's say you have a method like exponential smoothing, and then you have also a method in your organization, which is like the benchmark. Now, when you calculate the forecast, you want to report the accuracy against that benchmark. This is what we call the relative accuracy measure. So you can also develop that and write your own functions if you want to do something like that. Okay, so now let's talk about how we evaluate accuracy in Fable. This is extremely easy. There are a lot of work actually behind this to make it extremely easy. In reality, it could be a bit complicated, writing a lot of code, but here it made easy thanks to Mitch and everyone involved in this development. So once we have our model table, we pass it to forecast function, and then we get our Fable or forecast table. So how we evaluate accuracy using this function called accuracy. So we have the accuracy. It takes two arguments. It takes the forecast table, and it takes also the original data that we used. All right. So that is the data I had, well, somewhere here just to show you, but I will show you also an example a bit later. So here, this is my house production for the beer, but I filter the year to be just in this space. And I use this to fit my model, and I now pass the whole data, not just this part. And by doing this, it goes and matches the forecast that I generate here for the corresponding index to the house production, and then automatically calculates these errors, the accuracy measures, and then it reports all of them. So here you see also mean error. This is something that we call it a bias. So it's simply you take the errors and then you take the average of all the errors. But because the errors could be positive or negative, meaning your forecast is underestimating or overestimating, this may cancel out each other. But the average could be, again, a negative number or a positive number, meaning whether your forecast is underestimating or overestimating, whether it is positive or negative. Okay, so this is about the point forecast. Now, what about the distributional forecast, where we have the whole distribution, but also a prediction interval and a quantile? So how we evaluate them, how we know if a prediction interval is good or not. So let's start with the prediction interval. And let's start with a score for prediction interval called Winkler score. So what we do in Winkler score? First of all, when it comes to prediction interval, remember we have a coverage. And this coverage is determined by a value of alpha. So the coverage that we are talking about here is 1 minus alpha percent. So let's say if alpha is 0.1, then we have 90% coverage. If alpha is 0.2, we have 1 minus alpha 0.2, which is 0.8, so it is 80% coverage. So that's actually what alpha means here. So what is YT is the actual, what is LT is a lower bound, and UT is the upper bound. Now, I will show you in a minute an example, but just briefly to see how we calculated a score in each period. What we do is we go, so once we have our prediction interval, we go and then look at the actual. If the actual is within the prediction interval, then the Winkler score simply is the width of that prediction interval, the difference between upper bound and lower bound. However, if the actual lies outside the prediction interval, either below the lower bound or above the upper bound, we add a penalty to the width that we calculate. So we have, again, the width that we have, but we add a penalty. And that penalty depends also the distance between the actual observation and how far it is from the lower bound or upper bound. Let me show you, I think here, hopefully it makes more sense. So a new page. I hope again you see my screen. So basically I have, let's say this is my historical data. So I forecast for the next 3 periods. A little bit bigger. Okay, so these are my 3 points that I forecast for the future. And again, the historical, we use historical data to forecast the distribution, and from there I can extract the prediction intervals. And let's say this is the point forecast, and then now I have an upper bound. Maybe I'll use different color just to show you. So this is the upper bound for this, an upper bound for this, an upper bound for this, and then I will have also a lower bound. So a lower bound, a lower bound, and a lower bound. So, and if I link this lines, so this would be my interval basically for this. Okay, so this is maybe my prediction interval for 1 minus alpha percent. So how we calculate the Winkler score? So in each period, so this is my first period, this is my second period, this is my third period. So in each period, I go and look at the actual, basically. And then my actual, let's say I will show them with this. So if my actual is here, or here, or here, then I refer to the formula. So if the actual is within the interval, so the Winkler score is simply the difference between the lower bound and upper bound. The lower bound and upper bound. But here now the actual is outside. And because it's the outside, I have to go first calculate the difference between upper bound and lower bound. And now there is also a distance between what I forecast, I mean the actual, and also the lower bound. So this distance. So I have that. Now I add a penalty depending on how far this point, the actual point is from the lower bound. And then I add all these scores that I have and take an average of them, a simple average, and this will give me the score for Winkler for this particular method. Now, let me ask you one question. Which kind of interval do you prefer? Remember, this is something I called is a width. So width is basically the difference between upper bound and lower bound. So do you prefer to have a wide interval or a low interval? So if I do two examples here, let's say this is one interval and this is another interval. So which one do you think would be better? So narrow is better. All right. Okay, the first one. Why the first one is better? No, it's not about the margin of error. Um, well, in general, we think narrower is better. Let me tell you why we think narrow is better. Because imagine if I have to tell my manager this scenario. So I produce a forecast and I say, well, the demand for vaccines, I don't know, a BCG vaccine for November, I think it would be around maybe 200 doses. And then with a 90% coverage, I'm also sure that it could actually change from 200 to be maybe around 220 or maybe 180. All right, so this is the range I give. So my interval, the lower bound is 180 and it goes to 220 and the point forecast was 200. That's the narrow option. Now, what if I say, well, the point forecast is 200, but the lower bound could go to 10 and the upper bound can go to 1,500. It's very wide. So when it is wider, it's very difficult for a manager to rely on that and make a decision. So that's why we prefer the narrow. But now there is a problem. What if my interval is narrow, but then all the forecast, so this is the forecast that I generated, but when I reveal my actuals, all actuals, they lie outside the interval. So even if my actual is narrow, but it doesn't capture the reality. Okay, so that's a problem with narrower intervals. So sometimes we like them to be narrow, while depending on the time series that you're forecasting, they could be very different. So some of them difficult to forecast, so you need to widen this a little bit. But again, not too wide because if it's too wide, it's not very helpful. And this is an interesting discussion in probabilistic forecasting that we have. So we are interested in a forecast that is narrow, but narrow enough to cover the actuals. Because if it's narrow and doesn't cover any actual, then how helpful it is. So that's why I am maybe interested in something if actually it does this. But again, depending on how many periods that you have, this would, again, some of them would lie outside, but I want the majority to be inside. Otherwise, it's not really helpful. So that's the discussion we have between calibration and sharpness. So sharpness refers to how narrow or wide this interval is, and calibration is whether actually that interval covers my actual observation or not. So when it comes to probabilistic forecasting, we want to have a forecast that is calibrated, constrained on the sharpness as well. I mean, sharpness, constrained, and calibrated. Sorry. So we want it to be sharp, to be narrow, but we want also to cover the actual. So that's the idea of sharpness and calibration. So I want you to think about this a bit as well. So why we are interested in narrow intervals and what could be the issue with the narrow intervals and what we are interested in. So we are interested in the narrowest interval that can cover the actual observation. That's the ideal situation we are looking for. So now, let me just tell you one more thing, and then I think we can talk about other evaluating measures as well. So I talk about prediction intervals. When I have a prediction interval of, let's say, 80%, what it means. Because whenever you have prediction interval, and as you see in the visualization as well, so I have a coverage, 80%, 90%, 95%, and so on. So you can actually determine that yourself. What is the coverage that you're looking for? It is almost impossible to have a model that is 100% accurate. Again, the reason is very simple. Let me actually, while you're asking that question, let me tell you this. So every observation in your data, by both what you observe in the past and the future, so every observation, if we call that observation Y, is a function of two things. Let's call them Fx, and the second is epsilon. So every point that we see, every point in the data that you have, every point, every observation, you can think of that observation as two components. One component, we call it Fx, and another component, we call it epsilon. What is epsilon? Epsilon, we call it the irreducible error. Okay, we cannot do anything about this. Okay, this is irreducible error. Now, what is this one? Well, this one, because it's a function of x, it means for every observation, I could have some systematic part. That's what we have been discussing so far. You may have some trend, you may have some seasonality, you may have some predictors or external variables like population, like whether the month or the day that you have is includes holidays or not, whether the temperature is high or low, and so on. So this X means different terms or different systematic information, right? So our idea is to understand different systematic information, or let's say different terms that can link to the observation. So again, if you think about the question of vaccines, so I can tell you something about the consumption of vaccines, and that could be a function of different things. Maybe the history of how much vaccines we had, if the weather, maybe if it's a flood, whether that flood affects maybe the consumption in a particular week or months of that. Again, is a function of population, let's say of children under 5 years, and so on. So that determines my X. And then what we do is we try to get an estimation of that, basically. Because we don't know, we just get a sample of those observations and we try to estimate the relationship between them and then what we observe. And that's what we have been doing so far, actually. So basically, when you use ETS, when you use ARIMA, and so on, they do this. They try to estimate this. relationship between the different terms and different components and the actual observation. So that's why we have estimation for ALIMA, estimation for ETS, estimation for seasonal naive, estimation for regression, and so on. So each of them, they try to get a relationship, to demonstrate the relationship and model it. Now, there is another problem here, and the problem is it is unlikely that we could fully understand every single factor that affects that observation. So in a way, we try to get a good estimate of that relationship. What are the factors that are affecting the consumption beyond irreducible error? We try to understand that, but it is almost impossible to fully understand it. So in our estimations, you make also some errors there. However, this error could be reduced by having better models, the model that capture most of the information. But still, we make some errors. So remember, every time we use models, again, this is valid for forecasting, but any sort of machine learning model that you use, we have two type of errors. One is irreducible error, so we cannot do anything about it. And we have another one, which is reducible error this time. And how I can reduce that error? By getting better models, a model that can understand most factors and can describe that factors and estimate them better. So if you think about this, whenever you model, you have then two types of errors. Even if in ideal world, let's say, even if you get the exact fx for this, so it means you know exactly all factors contributing, you still have a reducible error. So that's why you would never get 100% forecast accuracy. And actually, that is why we also emphasize on always acknowledging uncertainty when it comes to the forecast and not just relying on a single number. So hopefully that clarifies that a little bit. So now let's go back to this, what 80% means. How much time I have? Okay, so I have some time. So can you tell me what 80% means, please, when it comes to a prediction interval? Because I want to also tell you something interesting here. So if this interval is 80%, so it means I expect 8 of 10 observations to lie inside this, but I expect also 10% to be here, so above, and 10% below. All right? And that makes it 100%. So I expect, so 10% could lie, the actual observations could lie below the lower bound and 10% above that. Now, if I add this 80% to 10%, I will get this. So this would be basically 90%. And actually, this 90% is a quantile now. So remember, I had the prediction interval, and then I just told you what it means. And then when I have an 80% prediction interval, it means there is a chance of 10% the observations lie below lower bound or above upper bound. Now, if I take the upper bound here and I add these two numbers, I will get a 90%. Actually, this 90% refers to a quantile. So this is actually a quantile. So in this way, you can see that there is a relationship between a prediction interval and a quantile. So this is one quantile, which is 90%. And actually, this one here This is a quantile of 10%. So again, this is another quantile of 10%. Just refer to it as Q10. And this one would be Q90. So in a way, when we talk about a prediction interval, there is a relationship between a given prediction interval and a quantile. If you have, let's say, a 90% prediction interval, so well, that means you have an interval. This interval is 90%, so there is a chance of equally 5% here, 5% here. Then the 90% prediction interval gives you a quantile of 95%, because then you will have all of this, and then a quantile of 5% as well. Okay, so just remember, you can go from a prediction interval to a quantile, basically, if you want. So let me go back to my slides just to complete that part as well. All right, so hopefully the Winkler score is clear. It's quite intuitive, I would say. It's easy to understand. And it is just a number that depends basically on the scale of the upper bound and lower bound. And how we calculate it, we take our fable, we pass it to accuracy function, we include the actual observations, because accuracy will use this to map the actual observation to the forecast that we generate using the index. But here I have to provide also what are the measures that I'm interested in. So I have to provide this argument, and I say I'm interested in the interval accuracy measures. That's how I provide it. And if I do that, then I get a Winkler score for each method that I'm using in my model. So another score that we use when it comes to evaluating probabilistic forecasts is a quantile score. So the quantile score is referring to every single quantile that you have in the distribution. So you can actually have any quantile in the distribution. Depending on your needs, you can go from a quantile of 1% to 99%, between quantile of 50%, anything that you are interested in. So how we calculate the quantile score? Again, we have an actual observation. And then here you have the P that refers to the quantile itself. So P is, again, going from 0 to 100%. You changed it from, let's say, 1% to 2% to 3%. And once you do that, you get the quantile value. Okay, so for each period and for a given quantile, you can calculate the quantile value. And depending on the value, whether it is smaller than the actual observation or bigger than or equal actual observation, we calculate the difference between the actual and that quantile itself. And then we multiply by 1 minus p for this one, and then multiply by p with this one. So again, if p, for instance, is 50%, which is a quantile equal to median, so this part would be basically 1 minus 0.5 is 0.5, multiplied by 2 would be just 1. And then this one, 2 multiplied by 0.5 would be 1. Basically, we have just the difference between these two. Actually, this should be an absolute value here as well. So the absolute value means the difference between the quantile and the actual observation. And this is similar to just an absolute value. In some textbooks, you may not see this 2 multiplied by 2. So here, people include this because, especially when it comes to the quantile of 50%, is interpretable. It is simply equal to the absolute error, the difference between the quantile and observation. So for each quantile, you can also calculate its score. And then we can calculate many quantiles if you like, either visualize them or simply take an average across all of them. And if you calculate every single possible quantile within a range, actually this is another similar to another score that we call it continuous rank probability score. So now we are somehow interested in the sorry, in the whole quantiles, the quantile range. So just to tell you what actually CRPS means, CRPS is a measure that we use to see how good the whole forecast distribution is. So intuitively, it is something like what we observe here. So remember, we used in Fable normal distribution. So when we have a normal distribution, we have a mean, and then we have a variance. So if you have a mean and variance, you can actually draw a density or a PDF, probability density function. So once I have the probability density function, I could also go and get the cumulative density function. So probability density function has a, like for a normal that bell shape, right? But the cumulative density function normally has this kind of shape because it goes from 0 to 1. So for each observation, we add up the probabilities. And because we are adding all the probabilities, and probability is between 0 and 1, at the end, it approaches 1. That's why we see here. So now how we use it to evaluate how good a forecast distribution is. Well, in this x-axis, you get the actual observations or the possible values, the possible values that you forecast. And then one of them could be the actual. Okay, let's say this is 10, 20, 30, 40, 45. So these are all possible values that I have in my forecast distribution. And then I have a likelihood for each of them, a probability for each of them. And I add up the probabilities and I get this uh, cumulative density function, CDF, for the red color. So the red color is the CDF, let's say, for one method. I could, let me see if I can draw here. So I could have maybe another method. So if, let's say, I have another method that has a CDF like this, I'm just not very good in drawing, but anyway, try. Okay, so this time, so this is for the, let's say, first method in red, and then you have the second method. So what we are interested in is the area between this red line and this blue line, let's say. So what is the blue line? The blue line is the actual. Okay, so now let me ask you this question. If this is the actual, what is the probability of that happens, that value to be observed in the past? 0. That's why. So you have 0, 0, 0. And then when we observe the actual, what is the probability of observing that actual? Well, is 1. Right? So that's why you have this vertical line. So it's go up to 1. And then the cumulative is going to be 1. So that's why you see this vertical line. So this is the actual. Now, when we have multiple forecasting methods, we get multiple distributions. Okay, distribution for method 1, oh, it shouldn't be like that. Not sure why it. So that's one distribution for, let's say, red. Another distribution for this black, and so on. And then for each we can get this CDF. So which one actually is better in this case? Well, the one that is closer to the actual. Okay, so if you get multiple of them, you are interested in the one that is closer to the actual. In this case, the black one is closer to the actual. So that means it has a lower CRPS. And this will give you more reliable forecast when it comes to the forecast distributions. So this is conceptually what CRPS does. So you can think of the probability distribution, convert to a CDF, and then for each period you have one actual observations, and then you compare the CDF of each method for that particular period, because remember, for each period I have one distribution. So we calculate the CDF and then the area under each CDF closer to the actual tells me what is the CRPS, or which method is better. So closer, if this line is closer to the actual, it means is a better method. Okay, so let me see what else I have here. It's moving forward. Okay, so now how we calculate the distribution accuracy measures, similar to the past. I have the fable, pass it to accuracy, actual data. Now I need to provide a list of measures, or just use measure in this case. I think it should work. So I have to say that my measures are distributional accuracy measures. And it will give you the percentile, or it is the same as quantile, and then CRPS as well. So again, here lower is better. In all error metrics we have seen here, the lower means better. So another thing that you can do, you can also calculate the quantile score, or even Winkler score if you like, for each particular coverage. So in some use cases, this might be relevant. For instance, if you are interested in using forecasting for inventory, sometimes in inventory we have a service level, and service level somehow could be related to the quantiles as well. So you might be interested in evaluating how good your model is in getting the 90% quantile right, which is relevant to the service level of 90%. And that's why you just go and evaluate the accuracy there, rather than maybe a point forecast or any other quantiles. So we could also do that here. So this is what we have for this one. I think maybe we can have like a break now, because after the break, I can go and start with the demo, just to show you with the data set that we take, how we actually do it. So can we please be back? So we have basically, let's say 15 minutes or around that time. So let's be back in 8. So I'll put it here in the chat. All right, so let me we are back at 8:40. So I'll be back at 8:40. If you have any question, or I could actually look at this as well. I'll look at the chat if there is any question, but if you have any question, please feel free to ask. If nothing, if there is anything not very clear, just let me know. Okay, so let me look at the chat. So I thought there was earlier a question. So Mitch, I think, answered, but so I think the question is about, yeah, what if I have exogenous variables or predictors? I think if you go to the apply exercise, so in vaccines administered, I have included deliberately a couple of predictors there. So there are a couple of exogenous variables. So hopefully that exercise will help you to use either dynamic regression that Mitch mentioned here, which you can use it with ARIMA function, or you could just simply include things in regression as well. So there are a couple of predictors there. I put them there, so you can try those models with the vaccine data in the apply exercise, and then later take the code and see if you can actually use it with any other data set, like what you have in infectious disease modeling. But I would say also infectious disease modeling is a particular sort of area that you cannot always do the time series modeling for that. But maybe you can combine it with other sort of modeling as well that is more tailored to disease spread and so on. Actually, one of my PhD students is working on an interesting topic about model portability, because in public health in general, uh, so people use different models for different things. So one idea we want to explore is it possible, or what are the features or characteristic of a model that make it portable across different domain of public health? So hopefully we may have something to share in the future about this. Yeah, so I will show you. Well, there are two questions here. One is, are there any requirement about the training data set size? Yeah, that's a very good question, Amal. Absolutely. So I will discuss after I show you a demo. I will discuss time series cross validation, which is the most reliable way to tell which forecasting model is reliable and good to be used in practice. Now, one constraint we may have is, what if my sample size is very small? If you have a large time series, um, and again, the large here depends on the context as well. But I would say if you work on monthly data and you have 10 years of data monthly, uh, then I think you can use um, enough data for train and test. So I will talk about that a little bit later. But as a rule of thumb, normally we can use 20% of your data in the test and then the rest in the training. You could also change that number to, I don't know, 25%, 30%. Sometimes maybe if I have monthly data, I just want maybe to test it in the last 3 years of my data. So I just take 3 years of data as test set, and I use 7 years as the training set, and so on. So that's, again, it depends on the context. For example, if I work in emergency department admissions or hospital admissions, normally I get about 5 to 8 years of daily data. So in each day, I know how many patients use the service in the hospital, and I have the data over 8 years. Uh, and I have to forecast for every 42 days in this case. So my horizon is 42. But what I want to always do is actually I use one complete year as the test set, because I want to test my model in all different days of the year. So that is what I do. But if my time series is short and it doesn't allow for this, so we have to do different things. One is actually relying on information criteria. So remember we said information criteria is a measure that tries to balance a good fit and penalizes the number of parameters. So one problem we have with overfitting is, as we increase the number of parameters, the model can actually improve in fitting. By the way, we can always get 100% fit by just adding more and more and more variables. But the 100% fit, while it fits the training data, it will completely fail when you use it in real world data to forecast the future. So that's why we are not interested in only fitting. So information criteria in a way balance that and try to avoid overfitting by penalizing the number of parameters. So it gets a balance of getting a reasonable fit that captures the information but not overfit. So if you have a shorter time series that doesn't allow for test, train, split, and doing this sort of thing. So maybe you just rely on something like information criteria. So another question is about is that this distribution forecast accuracy, can we say one is better than another? Yeah, so that's what actually I show you so far. So we have measures like CRPS. So we can calculate CRPS for each forecasting method and then compare which one is lower. So the lower means, a better. Or if you are interested in Winkler score about the prediction intervals, again, you can have a score of Winkler for each forecasting method. And then the one that has a lower score, it means giving you a better forecast overall. I will show you again in the next session how we do actually time series cross validation, and that help us to report also accuracy measure in a bit more detail as well. So now let's have a quick break. Maybe you can get something to drink or just stretch your legs, and I'll be back in about 5 minutes again. All right, everyone. Well, let's start the final session by first going through a quick demo of how we can do what we have discussed so far. And then following that, we can also talk about time series class validation, a bit of residual diagnostic as well. Well, let's first start with bringing in the FPP3 library. All right. And then let's use a data set that we have also used in the past. This time I'm going to use the retail data. And again, if you want to know what is this data, you can just use the help file and it tells you a bit of description about this. And there are different industry and then different states. So it's a testable, it's a monthly, that's what we see here. And then there are 152 different time series. Maybe what I would do is I would probably, let me just look at the house retail and see. I just want to see how many different industries we have here. So there are like 20 different industries. And then we can just, let's say, take the cafe, restaurant, and services. So I'll just filter that one. So I'll take this and then filter from the player in tidyverse. So I want industry to be the cafe, restaurant, and catering services. And actually, I don't want to look at any other things like states or whatever. I just want to get one time series to work with. So I summarize everything and then let's see what I had here. So I have turnover. I just take turnover to be the sum of turnover. So if I just do that, I will get one single time series that shows me the total turnover of the country for this particular industry. And let's put this in a new name. I just call it cafe retail. All right, so you know what to do next. So this is something that we have practiced a lot over the past couple of days. So I take my testable and I pass it to model. And then now I have to provide a list of methods that I want to have here. So if I do this, it will be similar to what we have done in the past, right? So again, I have the whole data and I pass my model into this and it will generate the futures for this from, if I look at the tail of this, so it will start generating the future observation. So again, from January 2019, February 2019, and so on, depending on the horizon. But what I wanted to do before actually doing this is to split the data into train and test, and then pass only the train data to the model, not the whole data. Remember, we split the data to train and test, or in sample or out of sample. So, and then we pretend we don't know the test set, so we don't use it to train the model. We just use it to evaluate the forecast accuracy. So for that, I first introduce a forecast horizon. And in this case, let's say I want to forecast for 12 steps ahead. And then after that, I will do the train and test. Actually, I put it here in the chat because I have written something that is generalizable, so later you can use it with your own data. So actually, let me put the rest of this so far. So sorry, this should be just everything that I do here so far, in case you want to maybe do it as I do as well. So I do a basic of test and train, and then here, let me just put it here as well. All right, so I take maybe my testable, and then I use filter index. Remember, we have used this before. Is a very good function, really useful to use when you want to take one part of your data set using testable. And this is especially useful when it comes to splitting the data into train and test and so on. So I have used something that you can use later, with your own data as well. So let's say if I have a data, let's just call it vaccine. So this is the name of my data set, and this is a testable. That's a requirement. And then assuming in this vaccine data, I have two columns. One column is called months, which is my index, and another column is called dose, okay, which shows the number of doses in each month that are consumed. So if I want to adapt this code to my own data, well, I come here and I change the cafe underscore retail to vaccine. And then if the name of the column is months, I don't change it. Again, maybe it's not in capital letter, is in the lowercase. I change that. So you just need to see what are the columns in my vaccine data set, and I update them here. The name of the column from the name of the testable that I have. So you do the same with the train as well. So vaccine, and then I replace here as well. And then I make sure that this exists in my testable as well. So you just need to replace these two things, and you should be able to now split your data into train and test with your own data set as well. So now let me run this too. Yeah, so here I think, okay, let me see that. So I have this, so the first one, let me just run this. Okay, so it says forecast horizon. I didn't run the first line, so let me do this and then again. So now if I go and look at the test, it actually shows me the 12 observations. So automatically it goes to the end of the time series and then comes and leave out the forecast horizons that I determine here. And I put it in the test set. So the rest of that from the beginning, let's say from the beginning of the time series to the early January 2018, it will be in the train. So I expect to see the end of my train should be December 2017. So this will match basically this now. So this is the end of my train, and this is the beginning of my test. So they should match. So this is like a quick test for me just to see that I did the splitting correctly. All right, so now I can actually go and do this. So instead of this time passing the whole testable, I pass only the train data to this. Okay, so this will guarantee that I use my test only for evaluation, for the forecast accuracy evaluation. All right, so now the rest of this is what we have done in the past. So I can have a list of models here. Like I will start with naive. And then here I will put the turnover, right? So because turnover is the response variable, the one that I want to forecast. And then I just keep adding basically things here. I just change this to be seasonal naive. And then this should be S naive. And then now if I want to add more models, let's say I want to add ARIMA. I'm just using an automatic ARIMA here. I will then use an ETS as well. And then changes to be ETS. Again, this is an automatic exponential smoothing model. I could add more. So let's say I could add also a regression. So I just type it as regression equal. And then let's just include the response variable and then a trend and season. All right. I could add more models, if you have more model, if you read also the FPP3 book, like the one with dynamic regression and so on, you could actually include more model. For instance, we have done decomposition, if you remember. So we could also maybe include a model for decomposition. So doing forecasting using decomposition, basically. So if this is something that you want to do, you can start with the decomposition model. And then here you have to say how you want to do the decomposition first. So there are different ways. We could use STL to do that. And then inside, I need to provide basically my response variable. And then I need actually to say what is the window for my trend. So this is something that Mitch has discussed as well. I just put some numbers. This is not necessarily maybe the best number, but and then this robust should be true. This is robust. So basically this will decompose your time series into trend, seasonality, and the remainder. So what is remain after taking out the trend and seasonality? So one thing I have to say actually here inside the decomposition model, I have to say how I want to forecast the seasonal adjustment data. So it means when I do the decomposition, so I can take out the trend. And then I could basically use something for that, and automatically it will do the something for the seasonality and put everything back, and I will get to the forecast using this method. So I just want to see if we include this, what happens. So one more thing that you could do, and we haven't really talked about this, but again, this is an interesting topic, is something that we call the forecast combination. So sometimes instead of relying only on one model, it would be useful to have actually a forecast combination of multiple models. So if this is something you want to do, is very easy to do that forecast combination using Fable. So basically, first you pass your train data to the model, a list of models inside here, and then you pass this now to a mutate function. And then I create, let's say, a new name. I just call it comp equal. And then now you can pick any model. I will just pick ARIMA here plus ETS plus, let's say, STO. So I take these three models. So basically, I'm combining the forecast from this. But now I have to divide them by 3. It means I give equal weight to all of them. So it is the simple average. So now I will get an extra sort of method that is not just ARIMA, ATS, or STL, but a simple combination of them. So when you have the forecast, you add them up and you get 1 and you divide by 3 to come back to the right scale. So let me see what happens if I do it. Let me just actually put this in a name and give it a name like fit, but let's call it fit basic to distinguish it from what I would do later. So if I run that, and then I look at this, now actually it didn't do the, is it over here maybe? Right. Yeah, so there was a typo there. Now I have one time series and I have 1, 2, 3, 4, 5, 6, and 7. You cannot see the combination model there. So I have the 7 models, I fit them in my training data. And then the next step, you know what you need to do. You just take the model table, you pass it to the forecast function, and then now I say my H is, instead of typing it to make it a bit more reproducible, I just do it here and I pass it to another name. Let's say call it FCST basic. That shouldn't be that, should be this one. Sure, what is that? Okay, so I take my model table, pass it to forecast, and I have already defined what is this forecast horizon, which is 12 period. And because it's monthly, it will forecast for 12 a step ahead. So if I run that, then I will get my Fable, and it is monthly, and I have 7 different models, and it is only one time series. Okay, now it comes the accuracy part. So when it comes to the accuracy, the first thing I have to do, I have to take my Fable, and I have to pass it to the accuracy function. Now, the first argument that I have to provide inside the accuracy function is the data that I have used. All right, so this is the whole data basically. And so accuracy knows now to compare the index, you know, from the data and from the Fable, and go and match them together and calculate the errors and the rest of it and report basically the error metrics here. So take the Fable, pass it to accuracy function, and then provide the actual data that you have before splitting inside. And then after this, you could do different things. Either you could say which type of accuracy you want. You want the point, interval, or distribution. So here I just go with like all of them, but you could later try and remove them if you like, if you want just to get the point forecast or whatever. So I have to provide an argument which is called measure. And now because I have multiple of them, I just use a list. So this is how you use it. Just type as I typed. And then now I need to say which kind of accuracy measure. So I want to have a point accuracy measure. I put a comma there, and then I want also to have interval, which is Winkler in this case. So interval accuracy measure. And then finally, I want also to get the distribution. All right, so let's call this again accuracy. So if I run this now, and if I go here, I get a list of all the models here I have, and then a list of different accuracy measures. Okay, so now do we need all of them? Well, it depends. Again, as I said, there is no best accuracy measure, but normally you can go and select some of them just to make the comparison a bit easier. So here I go and take, well, first of all, I take that model. So you don't need that type here because we just used out of sample calculation. That's why it tells you that this is only based on the test set. So I select this column using this function select, and then let's say I select mean error, I select RMSE and MAE, but you could select more if you like as well. Or just like, let's actually select Winkler. And then, well, this pinball is just a quantile score that I mentioned. So now it is a bit easier to look at. So some of these models, they are overestimating and some underestimating if you look at the mean error. And if you look at our root mean square error, so you have to see which one is the lowest. It seems like ETS in this case has the lowest error, but it is very close to the combination. And then following that, well, again, if you look at the mean absolute error, it seems like it's quite similar. But then if you look at the Winkler, the story is a bit different because ARIMA is doing better for the particular alpha that we have here, is 90%, I think, by default. And then we have the quantile score here as well. And then I could also select CRPS to see everything. Let's actually put CRPS as well. CRPS. So when it comes to the probabilistic distribution, so as you can see, you can compare. It seems like combination is doing better comparing to the others. So if you go just for the point forecast, I think a combination or ETS is better. But then when it comes to the different quantiles that you are interested in or the whole distribution, the story could be slightly different. Still, some models are very close, like STL and combination. They are actually not very far. And this is where, I mean, here we just rely on forecast accuracy and error metrics. But as I said, I don't know. Would there be any difference if I use STL or if I use, let's say, ETS? They are a bit different, but would actually they make a difference if I evaluate them based on the decisions or the utility of the forecast? I don't know. I have to do that optimization and simulation and evaluate everything. And that's a bit expensive. It takes time and so on, but it may be worth the effort. However, it might not be easy for everybody to do it. All right, so that's basically how we do the first part, which is splitting to train and test, and then fitting the models on the train, and then evaluating the forecast accuracy, and then reporting the forecast accuracy and see which method is giving you the lowest error metric. Okay, so let me share the code that I have so far, but we also put the code. Okay, so this seems like it's a bit too much. Okay, and then this is the second part. we will share the code like what we did in the past. So now let me actually go back to my slides, because so far we just did a simple split of train and test, and the test set was equal to the forecast horizon. Or maybe I will share again my whiteboard. Okay, let's actually do this. Let's have this, and then okay, so what we have done so far, I wanted, in the example I showed you here, I wanted to go and do the forecast for 3 steps ahead. So 1, 2, and 3. And I said, well, because we cannot wait to observe the future and then tell people how good the forecasts are, we come and say we use what we got. Okay. And with that, we said, let's start with leaving out 3 period and then fit the data and the rest. Okay. So this is what I got. So this was my train and this was my test. And then I did the calculation and report the error metrics. And then I can now tell you which method has the lowest error, depending on what we want. But there is a problem with this. And the problem is a bit logical as well. Can you guess what could be the issue if I just do this and rely on this to tell people, you know what, I did split to train and test. The test size is equal to my forecast horizon. I did the calculation. Naive is the best method. Go and use it to forecast the vaccine needs. I'm sure it is the best one because I did the calculation. So what would be the problem with this argument? How confident you are that actually this method is really good for the data that you have? Can you share your thoughts in the chat, please? Can you think of any potential issue here? If I just do this and then tell people this is the method that you use, I'm sure. And actually, this also goes back to a question we had earlier about what if an event happens within this period. Somehow it is related to that. So my question is, what is risky with doing this? Well, let me tell you what is the problem here. So the problem is, if I just do this and tell people this is the method you have to use, it is a bit too risky. Why? Because I am just relying on evaluation on 1 step ahead, 3 step ahead forecast. To be more certain and more confident to tell people, go and use this method, I need to test it in more observations, in more situations in a way. So more observations mean more situations. And that goes back also to the question. Maybe I'm lucky. There is nothing special happening in this 3 period, and my model is doing great here. So I was lucky. It was not because the model was good. So that's why I need to test it over a longer test period. And then make sure now it has seen different situations. When I refer to situation, I mean different period, because maybe January would be different from February. Maybe something happened in March. You see what I mean? And typically, I want to test it even if, let's say, this is a monthly data, I want to test it in a couple of years of data. So what is the solution? The solution is, instead of saying my test set, because the test set is 3 here, and my forecast horizon was 3. So instead of saying my test set is equal to the forecast horizon, basically I go and I increase my test set. So the size of my test set, I will increase it to include multiple 3 steps ahead. And this is where I said you can go and say, I split my data. I mean, let's say 30% of my data would be in the test set, and then 70% of my data, as a rule of thumb, would be in the train. Okay, so now I increase the test set, and I will show you what we do next. Now let me tell you something. This initial train, later we refer to this in Fable as this dot init. Okay, so if you see an argument that init equal, let's say, something, it could be a formula or it could be just, let's say, 30, it means this is the size of my first train. It has 30 observations in it. All right, so we start with that. So we fit a model on the first train, and then I forecast for 1, 2, and 3 periods. Now, there is another argument that we use later in Fable, and it's called that step. So that step is, in this case, I will just say is equal to 1. So in each step, I go and take the previous train session and I add 1 period to it. So basically, I increase the size of my train by including 1 from here. And then I forecast for the next 3 periods. So now it will be 1, 2, and 3. Okay, so in each step, I add 1 period to this. Actually, I keep doing this. So I take the previous train, which was up to here. I include 1 more observation. I forecast for the next 3 period. And I keep actually doing this, adding, until when I just have only 3 observations left at the end. So that would be somewhere here. Let's say I have 1, 2, and 3. 1, 2, 3 observation left, and then the rest would be my, so the rest would be my train. Okay, so between you will have more, let's say. And then I have to stop here because if I continue, then I will have only 2 observation, but my forecast horizon is 3. So I have to stop here once the remaining number of period equals to the forecast horizon. So by doing this now, I have more errors. And then I will test my forecasting methods in more situations. This is one situation, another situation, another situation, another one. So I will have the opportunity to test my model in multiple periods, multiple different periods. And if my model performs well now, I'm more confident to tell people because I have tested it in different periods. So there is the first one, it was really risky to tell people use this model. Now we have less risk because I have tested it already in multiple situations. So I will get, let's say, error 1, error 2, error 3, because now in each period I reveal the new observation. And then after some period, now I reveal everything from the test set. So I will have also the actuals in addition to the forecast. So I can calculate the errors. So each time I arrive at some point here, so I reveal all these three. I reveal all these three. So these are my actuals. And then I go and then I calculate the error difference between them. So I have now one set of error for this one, another set of error for here. Okay, and so on. And then now for this, let's say I can go and calculate RMSE or calculate RMSE until the last one. Or I could even do this. I can actually take all these errors here and calculate RMSE. And this would be for each horizon. And then RMSE and so on. Okay, so, and then if, let's say I do this, so I calculate an RMSE for the first, the second, the third. At the end, maybe I can take an average across all of this and I get one score for that are tested in everything, every situation. By the way, there is a name for this in Fable that we see later. We call them ID. So you will see later, you will see a column called ID. So we call this ID1. This would be ID2. This would be ID3, and so on. Okay, so just remember what that init is, what that step is, and then actually what ID means here. Maybe just to make sure everybody understands what we do, I can also show you quickly what actually we do here. So imagine this is a testable. Okay, so this is a testable. This index is months, and then you have a measurement, which is demand in this case. And let's assume, again, we do the forecast for 3 steps ahead. So if I do the forecast for 3 steps ahead and I would do the basic split, I just leave out this. I just hide them somehow. I'm not sure what is the best thing to hide here. Maybe this. Okay. So the numbers are there, but just I hide them. I pretend I don't know them, right? So if I do this, this would be a simple train and test. But now I want to do something more. And this is an idea that we call time series cross-validation or forecasting with rolling origins. So both refer to the same thing. So now I come, instead of leaving only 3 periods, because my forecast horizon is 3, I just leave a bit more. But as a rule of thumb, as I told you, 20% here, 80% the rest, or 30% here, 70% the rest. So now I pretend I don't know this. So this would be the size of my initial, so that init would be this size, which is 17 in this case. So later I introduce a function that you can use easily, and the function, what it does is this. It takes this basically, and it goes and introduce a new column called .id. And now this would be 1. Okay, so, and the function will treat this as one separate time series. So it will go and fit a model on this. And then let's say if I just use naive, it will produce the forecast for this 3 period. And then the forecast for those 3 periods would be something like this. I just separate it in a different color for us to see this is a forecast. So what is the next step? I reveal, well, you know what, there is no need to even hide this periods. It's up to you, but I will just go and reveal here the next period. So now I take everything and then again there would be an ID. This time my ID is 2. And if I use again the uh, naive method for this, so this would be my forecast for the next 3 periods. So you see they have something in common every time. This is, and I just add one variable, one observation, and then fit models and continue. So later, because we do fitting and forecasting separately, first we do the time series cross-validated. So basically, you would see something like this. So you will see this, and then now when I reveal this, then you'll see an ID2 here, and then this. So you'll see a very long, um, table, but you'll see something like that. So if you see this, you need now to make the connection between what I have explained so far, and hopefully you wouldn't be confused by actually what is this ID and why I have 1 and 2 and 3. So now every time I have a sort of a new time series identified by ID, and then I can do forecasting for it. I can fit models on it and do the forecast accuracy calculations and so on. Okay, so now let me see what I have in my slides before I go and do a quick demo there. So this is basically what I have tried to explain. So I have my past data, as one of you said, what I got so far. This is my future. And then to start with, I split with test and train, but then there are some limitations with this. It is too risky to make a decision to tell people which model is the best. So that's why I go and split basically the data into train and test. Some people even do it in train, validation, and test, but we don't need to do that here. And then this is the idea behind time series cross-validation. So this is my whole time series. I first split it into a train and test, where the test set is bigger than the size of the forecast horizon. So it shouldn't be the same size. It should be bigger, and actually much bigger, not just if the forecast horizon is 3 and the test set is 4 is not very helpful. So I start with my initial number of observations, and then I forecast for the next period. And this is for 1 step ahead, but you could do it for 3 steps as I did there as well. So here we introduce a new function called stretch testable to do what I explained. Okay, you just provide the arguments and it does the whole thing for us. So later, I think in the apply exercise, you have, because when you do forecasting, if you have predictors or exogenous variables like population, like temperature, weather, and so on, you may need to produce a forecast value of those predictors to use in the forecasting model. If that is the case, so you may need to use one of this as well. But anyway, that's the exercise. You will try to see how you can manage it, and you will get a solution for them at some point as well. So you'll try first. Hopefully you succeed, but if not, we provide you with a solution as well. I will actually do one. Let me see if there is anything new here. Otherwise, I will just go and show you how we do the coding there. Because yeah, so all of this is something that I have explained. So let me go back to my RStudio session. Okay, and I'll try to add some comments to this as well and send it to you later. So now let's try the time series cross-validation and see how we can do it. So everything we do is similar to the basic one, except the split. So we first do the split, and then we do the rest of it. So the first thing that I do in the split, I actually define a variable called percentage test, because I just want, again, make this automatic in a way, and you can change the percentage from 30% to 20% to 15%, depending on the size of your data. And then you see the result changes automatically. So I define this variable. And then following that, I do something similar to what I did in the first one when I split the data here to train and test using, this. So again, this is just a notion of filter index, how we use filter index. You just go and look at here. So what is important to remember in filter index, you have this tilde and you have this point. So if you see a point at the beginning, it means from the start of the time series, and then tilde means until this part. And the reason we do this as that character is because this needs to be inside quotation marks, like you see here. It's why we use as that character. And then if you see that first this and then a tilde, and that means from this particular time period until the end. So this points there mean end here, and if it's at beginning, it means from the beginning of the time series. So I now need to do something similar to it. It looks a bit tricky, but it is not really. It's simple. So let me just share that in the chat as well. So if you want to do it, all right. So I just put it here. So again, it's similar to what we have in the past. I just wrote it in a way that you can use it with your own data by replacing what you need to replace. So here, if you again got your own data, which is vaccine, and given that vaccine has two columns, one is months and another one is called dose. So you have to come and say, well, this is the name of the current testable. I will have to replace it with my vaccine, with my vaccine. And wherever you see this, you do that. You can even do a Control F basically, if you want to replace everything with your own data. So you say, wherever you see this cafe retail, just replace it with my own name here. All right. And then, for instance, here in cafe retail, I have months, but if you replace it with vaccine, and in vaccine, the name of your index is not months, but is quarter, for instance, or is date, you just replace that with that. Okay. So wherever you see that, you have to do it. So you just update the name of the testable and the name of the index, basically. And you just run. So let me now run this. Just delete one of them. All right. So now if you look at the test and train, let's say I just look at the train. Again, I split it based on test and train. And this would, by the way, would work with many time series as well. So here I have one time series, but maybe if I have time, I will change it to many time series here, because if I don't do this, I just use aus retail. Basically, if you do that, you replace cafe retail with aus retail, it would also work. So the split would be done nicely without making any changes. So it is just written in a way that is helpful for you in the future as well. Okay, so what is the next thing that we have to do? So I split first into train and test, but remember now the test size is 30% of the total length of the time series. It knows it from here because I say, look at the total length. So I take, to do the cross-validation to get the IDs, I take basically the data by testable, and then another thing that I have to do here is I have to pass it to another function. And this is because, remember I said you keep creating these IDs, but at some point you have to stop. When we stop, when I have the number of observation left equal to the size of forecast horizon. And to be able to do it, again, I put this here in the chat as well. So you could just follow this line of code. So this filter index part here, it actually it guarantees that I will stop there. I wouldn't go further. That's what I put it here. But the most important function here is this one, the stretch testable. So remember again, dot init, an example I gave you, and also dot step. So here I don't provide a number. Instead, I wrote a function that goes and takes the size of the initial train automatically. And then that step is equal to 1. You know, in theory, you could change it. And this dot step sometime could also refer to the frequency of generating the forecast in your organization. For example, if you generate the forecast for the next 6 months, so that forecast horizon is 6 months. Now, the frequency is slightly different. The frequency is how often you generate the forecast. If you generate it each month, then that step is equal to 1. But if you generate the forecast now for the next 6 months, and the next time that you generate the forecast is actually in the beginning of this month 7, then you can change this to be 6 as well, because you generate the forecast every 6 months. But just leave it for 1 is not, I think it is better actually to have 1, because you evaluate it in every single period multiple times. So that's the first thing we have to do. And if you run that, now you will see those IDs that I mentioned. So now I have my index, I have the measurement, and I have the data ID. Again, is monthly, and then I have 128 IDs. This is actually good because I can now test my model in different situations. And remember, each ID refers to different periods. They have some period in common, but at least they get one period that is different from others. So it will be tested in different situations. So now the rest of it is similar. So I just go back. So what I had here, I just copy this and then paste it here. Once you feel comfortable, writing codes in R, you really have to use this copy paste feature, because it helps a lot. And then, as I said, maybe if you can remind me, if you haven't done it yet, I will share some links how to integrate GitHub Copilot on R Studio, because the auto completion is really helpful as well. Or I don't know if Mitch is there and he can share the link. Otherwise, I will share it later. So, okay, now, so I copy what I had before because I don't want to repeat typing everything there, because I need just to change a few things. The first thing I need to change is the train, because now I'm not just training on the split of train and test, but I'm actually training my model on different IDs. So I have to replace this with a time series cross-validated or the rolling origins. Okay, so that's the only thing that I need to change here. And maybe I just delete this basic and I just call it fit here. So I run this. Okay, I think let me see what I mistyped this one. Just do it again. And now you see it takes a couple of seconds maybe, because now I have 121 different time series and I have to do all these models, and some of them they are automatic and it will take time basically to run this. So depending on how many time series you have, you need to think about this as well, because sometimes computationally it could be expensive. So let's wait for this. And then while we're waiting, actually we can do also the forecast, because the forecast is easy. We just take the fit, which is the object I have here, and then pass it to the forecast function. And then my horizon here is again the forecast horizon that I had. And let's call this FCST as well. So I'm just waiting for this to fit all the models, data, and the time series cross-validated data, and then pass it to the forecast. Not sure what is going on here in the screen. Okay. Okay, so as I'm waiting for this, I can also write maybe the accuracy, because it's very similar to what we had before. So let's go back to see where is the accuracy. I just copy what I have written already here. And then I have to just replace the forecast object I had before with the new one. And I don't change anything else. Okay. All right. So now I got so I look at the fit. So you see now I have many rows, because I have different IDs. So each ID is treated as a separate time series. That's why I get now 121 different rows and then different models. So now let's pass this to the forecast function and then go and calculate the accuracy. Right? It seems like we have the forecast as well. So again, I have the that ID. This is like a key, basically, similar to what we had in Tissable. So I have each time series with a different ID. So for each ID and each model and each forecast period, I will get a distribution, and then I will get a point forecast. And it's quite a long table, over 10,000 different rows. So if I go and run this code now, I should be able to get also the forecast accuracy. So now the forecast accuracy is average across all these IDs and horizons. So because we will get only one score per method. Okay, so if again I focus on maybe this one. So you get one score, but remember we had 121 IDs, and each time we had 3 steps ahead 12 step ahead forecast here. So the score we get here is averaging across everything. And again, if you go and compare now, you see first of all this score change comparing to, I don't know if I can show you what we had before. I don't actually see them here. But if you compare this with what we had with the simple train and test, you see that these are different, and actually the conclusion might be also different. But I rely on this one because I have tested it in many different situations. So let's say if I use RMSE to judge which method is the best, these three methods are quite similar. ARIMA, combination, and ETS, they have a very similar score, both in MAE and RMSE. Well, with ETS being the lowest one here, well, this is a bias. All of them, they are actually positive, meaning underestimating in this case. And then we have a Winkler. So again, Winkler is quite similar to others. In this case, estimation of Winkler or prediction interval for the combination method is slightly better. When it goes to this one is ETS for the quantile score. And again, for CRPS, they're quite similar, slightly better for the combination. Okay, so but remember this one is average across everything. I now want to show you a bit more detail. What if I want to report this accuracy maybe across different IDs, or maybe what can I report accuracy average across all IDs for each horizon? This is another way to report that. So I will show you this, but maybe before going there, sometimes you may want to uh, report forecast accuracy for a particular Winkler score or a particular quantile score, or any score. Basically, you can actually extract things individually as well. So let's do one for Winkler and quantile in case at some point you may need it. So again, I take my fable, I pass it to the forecast function, and then I type the name of the uh, testable that I have. And then here I have to type function called list. And then here, this is a name I provide. So I want to calculate a Winkler score. It doesn't need to be a function here. Okay, so this is what I need, but I need also to say what is the level that I want. This refers to the prediction interval, let's say 95%. So if you do that, you can actually go and say, if I'm interested in 90% prediction interval, how these models perform in that case. If you want to do something similar with the pinball or the quantile score, so you can do something like this. So I just replace this because the rest is similar. Instead of having that name Winkler, I have this as a QS, a quantile or pinball, whatever you name, put it there. And then here I have to just type quantile score, similar to Winkler score. And then here I have to put a probability now. So what is the quantile that I'm looking for? So again, if you do that, you also get the accuracy measured on a particular quantile. All right, so you can do this actually with any measure that you want. So now let's move on and do a bit more detailed analysis of the errors. So, and I want to do first an accuracy report based on each ID and model. Okay, so what do I need to do here? I do something similar. So first I take my fable, I pass it to accuracy, and then I have my original data. So far, nothing different. So I do this for point forecast, but you can repeat this for others if you like. And then what I do here is I have to introduce a new argument called by. And then here I say, I want to calculate the accuracy, but this time I want you to calculate this by model. So that model, because if you look at the forecast table, I have that model, and I have another column, that ID. Okay, so I want to calculate the accuracy, but not just the average across everything. I want for each model and each ID, I want to have an error metric. This is how you provide the argument. So let's just call this, or just call it accuracy by ID. So if I run this, so I get something like this. So for each model and each ID, I have the report of accuracy across that 12 step ahead horizon. So each score now is taking the errors in 12 step ahead and then calculating the score based on the formula. So now I can do some visualization with this to reveal some information. And I do this with ggplot2. So I take basically this table that we see here, and then I go and create a ggplot. So when I do that, it means I'm using this data. So my data is here, or if you want, this could be just like this. My data is this table that we see here. And then now my mappings are, so I want to put something in X and I want to put something in Y. So let's say I want to, from these measures, let's just focus on RMSE, but you could do this for any. So I want to put RMSE values in X-axis, and then I want to put models in Y-axis. But if just to do something a bit more clever, I would say, I just don't want to put models, I want to also rank them. So that's why I can use this function called FC, FCT reorder. And then I say I want to rank this model based on the value of RMSE. And now the thing is, if I just look at one ID, so I have one measure, but because I have many IDs, one way to have a good visualization is to use um, a plot that help us to visualize variation. So I want to see how this error varies across different IDs. And you can do different things, but maybe you can start with a box plot, or later you can do density plot or any other sort of plots that you want. I just want to also use one of the themes that I am interested in, which is theme view. And let's see what we get here. Okay, so is it because maybe let's load tidyverse as well. Okay, I'm not sure actually what I mean. Okay, I can now maybe leave this out just to see what was the problem, or if Mitch is there, can tell me maybe. One parenthesis extra. What I'm what I'm doing wrong here. Okay, sorry. Data is that. Okay, that's correct, I think.
Bahman, you got a typo on data.
Sorry. Thank you. All right, so data is that, and then, so I think that FC. Okay, let me just go back. I think that should work now, maybe. All right, so let's see. Okay, actually I got what I want. So you see now I get a distribution of the errors for RMSC, and you can make this a bit better with better labels and so on. But it just tells you an idea of how this error varies across different IDs. Well, if you have a model that is consistent across different IDs, maybe that is a better model. But then you have a model-like regression that actually makes some big errors here. So that's why it's not doing well in this case. It could be because we have, I think, a multiplicative seasonality in the data. But anyway, my idea here is to show you another way of reporting your accuracy rather than looking at the total or the average score across everything. You can actually come and say, well, I just want to see whether the models that I'm trying to use, they are consistent across different IDs. So different IDs, remember, means different months, different situations. So in this case, it seems like ARIMA, ETS, and Combo, they are better than others because they have a smaller median, but also less variation. Well, they have some, all of them actually, they have some outliers, so big RMSEs. So if you want, you can also go and investigate for this particular models where they make these big errors. So in a way, you can also use this as a diagnostic tool to go and see, well, it seems like there are a couple of IDs. I think in this case is about 7. So there are 7 IDs with these models, they make big errors. Maybe you can identify which periods are those. There might be something you can do in the modeling to improve that as well. Okay. So I could do also something. I think I have a couple of minutes, so I just want to maybe actually show you this. I will send you the code so you can try it for yourself as well. Let me see. I will just, okay, I don't know where I have left this, but so let me put the rest of this code, the chat, in case you want to try it as well. Okay, so all right, so this is part of the code, and then there's, so here I use a box plot, but you could use maybe a density plot or any other sort of visualization to visualize variation or uncertainty. So you could also try this. I will show you quickly what it means, the last part of the code. So another sort of reporting that you could do is, instead of doing it for model and ID, you could do it for each model and across different forecast horizons. So this is also interesting to see how error changes going from 1 step ahead to 2 step ahead to 3 step ahead and so on. So this time I included all measures. So you could do exactly the same here as well. So if you want to include all measures, you just basically do it. So if you don't do it, it will be just by default the point forecast. But if you want to have all of them, you can also do this. So here I just replace ID to be H basically. So if I run this tool, let me see what I get. Do I miss something? Maybe. Ah, okay. So there is something that I need to do actually before this, which is this part. So I have to calculate a new column called H, and then do the rest of it. Because that column H doesn't exist, so I have to first calculate and then say now do that based on this column H. So now you have to see a time plot. In x-axis you have the horizon, and then well this scales, they're not good, so you have to have 1, 2, 3, 4, 5, 6, it goes to 12 step ahead. So it gives you an idea of, if you look at the different methods, how actually the accuracy changes over time. And it is natural, to see that for most of this models, the accuracy decreases. So RMSE increases over time because longer horizons means more. But also some of them, they are less, they don't really follow this pattern. They fluctuate a little bit. They may also signal something that they don't, they miss something in certain periods that we forecast. That's why they fluctuate a little bit as well. So this is another way to report forecast accuracy. So how accurate these forecasts are across different time horizons. So I will also, add comments here and then share this script with you. And I think you should have this by the end of tomorrow, I would say, in the website, so you can use it as well. So maybe very briefly, I go back to my slides and I can finish. Or do I have time? Sorry, I'm not sure how much time I have now.
You've got about 20 minutes left.
Oh, okay. So sounds good. I thought we have to finish at 10 o'clock. All right. So basically, this is what you need to do when it comes to evaluating the accuracy of your forecasting models. So as I said, the most reliable way is to use time series cross-validation. And this is, what we have done so far. So now what time series cross-validation is. So as I said, another name for it is forecasting with rolling origin. So we do that rolling in each period. And if you do this and the model tells you something, it is reliable. So you can actually rely on that. So this is the best practice. You have to do this every time that you want to report forecast accuracy. So there is now another thing, because remember at the beginning, I talked about two aspects of having a good model. If you care about forecasting, the most important one is actually the time series cross-validation. So that's what we really care about. Apply time series cross-validation, calculate the error metrics, and then based on that, decide which method you want to use. So that's the most important aspect of how good a model is in terms of how it performs if I want to use it to forecast the real future. But there is another aspect based on the residuals. So the residual is simply the difference between observations and then fitted values. This is only on in sample, all right, is just the training or in sample. This is not based on out of sample or the test set. So we calculate the difference. And then now there are certain assumptions when we do forecasting. So the idea is to make sure that these assumptions are valid. Because if they are not valid, then the model that we are using, they're not reliable. And reliable in different ways, because if we have the residuals, those residuals must be uncorrelated. So if you see the residuals, they are not correlated, and they don't have a mean close to zero, it means they are missing something. So they are missing certain information that are not captured by the model that you're using. And this is also what Mitch discussed in the white noise process. So we expect our residuals to be like white noise. So uncorrelated and with mean 0. So there are some other assumptions that are more important when we care about the distributions. And that is the assumptions of normality and having constant variance. So the variance of the residuals is not changing over time. Basically, it's like random. So if these assumptions are not valid, uh, the probabilistic forecast that you generate might not be very reliable. And that's why we say, let's say one option is if these are not normally distributed, so you may switch to using bootstrapping to do your forecasting. So here is an example of a Facebook closing price for different years and trading days. And then, well, here we just, do some calculations to update a testable based on the trading days right from the beginning. And typically for this kind of time series, naive is a good approach to use. So we take our testable, we pass it to model and using naive to forecast. And then if you look at the augment, so this is the function basically that is helpful here. So augment gives you this output that has the fitted values, but also residuals. So now when it comes to residuals, you see actually two columns here. One is called .reset and another one is called .inov. So in this case, as you can see, they are the same. There is no difference. But in certain cases, this could be different from .reset. And in some cases of exponential smoothing models, uh, where we have multiplicative cases, this could be different, but also if you do a transformation on the response variable, you will see a difference. So when it comes to looking at the residuals, you have to look at the .inov. If they are the same, then of course it doesn't matter. So in this case, .reset or .inov is simply equal to the observation minus the fitted values. All right, so we can create this visualization where we have the actual data and the fitted values, and then in x-axis we have the trading days from the beginning, and then the close price in the y-axis. Because this is a naive method, it follows quite closely the actual data, so that's why you see the fitted and actual, they're quite close. If we maybe zoom in a little bit, not looking at everything, but a part of data here towards the end, basically that's what you see. So you see that it's one leg behind because it is naive forecast, and then the residual is simply the difference between the vertical difference between these two lines. So I calculate in each trading days the value of the data minus the fitted value, and then this will give me this residual here. So a residual is like a time series as well, because in each I have periods and I have a measurement, which is the value of residual in this case. So remember we said, based on the assumptions that we have, you want our residuals to be like random, to look like random. So it seems like here most of the time it is, and except maybe this point that is missing something important. But also if you look at the residuals here, it seems like here the variation increases a little bit comparing to what we have here, which could mean the variance might not be also constant. We can look at the distribution using histogram, geomhist, and this will have an argument. Either you can provide the number of bins that you want to see, or you can provide the bin width, the width of the bin, and then you can see that. It's always good to play with the different bin widths to see, because sometimes histograms, depending on the width of the bins, they may hide things as well. So it is good to play with different bin size and see actually if they are hiding something. But here, this looks like a normal distribution here, but you see there are some points here and here as well. This one is the one that we saw previously, that it has a large residual here, which is negative. But if you look at the ACF, so hope you remember how we interpreted this, but we want actually, or the leg of this to be inside, this hash blue lines, dash blue lines. So if they are inside, it means they are not significant. So it means there is no correlation, autocorrelation in the residual of the time series. So here you see that there are two legs in the residual that touch actually those blue lines, or almost past here. So it means there might be those legs that are significant. But given the number of legs that we have here, maybe having one or two that is outside is normal, because we have an interval here, and that interval has a coverage as well. So having a couple of legs outside based on the numbers that we have here is okay. So when it comes to residuals, we assume that they should be white noise, uncorrelated, mean zero, and constant variance. So if that is not, it means some information is left in residuals that could be used in the model. And probably that is one of the most important insights that you can get from the residuals. So if you have a residual that actually has a pattern, clearly not random, because the one that I showed you, is a bit tricky. It looks like random, but there might be one, two instances that make it a bit not like that. But sometimes when you do the modeling, you see sometimes residuals that are actually, they have completely a seasonal pattern or a trend maybe in them. And if you see that, that's a clear indication of, the model that you use is not capable of capturing the information. So you need to look for something better. So you can do it visually. This is another function that you can use for that. So when you have your model table, you can pass it to this function, ggts residuals. So you get all of these three together. So you get the time plot of residuals, you get the ACF of residuals, and you get the histogram of the residuals, and you can look at them together and see whether actually uh, the assumptions that we have are valid or not. But you could also do a formal statistical test for this. And there are a couple of different tests. One of them is a long box test. And here we have an R that refers to basically the autocorrelation. So we have the correlation in each leg, those vertical lines. So each R refers to one. So this is R1, R2, R3, R4, and so on. So we can actually, based on that, we can go and calculate this statistic where L is the maximum number of legs. So there is also a way to determine maybe what would be a maximum number of legs, but you could also try a different one. I think one thing that we use in the Fable package is around 10, but that depends also whether your data is seasonal or not seasonal. So when we have this statistic, of course, if all these are small, it means they are inside those blue lines and maybe very small, then you will get a very small Q. But if these R's are big, you will get a large Q as well. So this is one thing that Professor Heinemann did. He maybe did a couple of experiments, and then he realized if you have non-seasonal data, that shouldn't be actually H here, it should be L. So that L could be 10, and then if you work with seasonal data, then the L here is not H again. L could be 2M, with M is the number of season that you have. 4 for quarter, 12 for months, for instance. And then we can actually have this test done using the functions that we have seen before. So you can use the model table, pass it to the augment function, and then use the function called features, and then pass that reset to this, and then say I want to use a long box text and provide the number of legs that you want to consider here as well. And this will return this table where you have the time series, the model that you fit. This is basically Q, the statistic that we have here, and this is a p-value. So this p-value also can tell you something. If the p-value is smaller than 0.05, it tells you that I cannot distinguish this from white noise. So if it is bigger than 0.05, it is indistinguishable from white noise. So it means it is a white noise. I cannot say otherwise. But if the p-value is very small, smaller than 0.05, so it clearly tells you that the residuals that you have here, they are not white noise. All right. So again, I repeat, if you have a small p-value, it tells you that the residuals that you are here are not white noise. All right. So I think with that, maybe we cover almost everything that we wanted. So now you have, the exercises in both learn and apply. And I think you can apply what we have covered so far and those data and beyond. And I just wanted to reiterate that, what we have covered so far is just a foundation. So we hope that this 5 days, 5 half days, give you a strong foundation to understand forecasting, to do basic things. What we have covered so far, you can do already a lot of things with this in practice for your work, if you are a student, if you are doing research and so on. But we hope that you keep also learning. So you use this, you have free resources online available, you have the materials in the website that is available. We provide you with 2 sets of exercises. So there are plenty of things that you can try really. But my recommendation is also try to see if you have a data set related to your own work, and then replace the data that we have used in the exercises or in the coding that we have done with your own data, and try to do things with that. And I think this would help you enormously to progress faster and do something that is helpful as well. So I don't know, Mitch, do you have anything, Henry?
I don't have anything more to add for content, but I do wanted to thank everyone for sticking it through, and I hope that you learned a lot about forecasting. Henry would like to share some information with you about surveys and some post-workshop information. Henry, are you there?
Yeah, Henry's there. I mean, I can see he's there, but Henry, we can't hear you if maybe you
I
are
see. I need to give Henry permission. 1 minute.
all right.
There you go. You should be able to unmute yourself.
Hi. Can you hear me?
Yeah.
Hello?
Yeah. We
Yes.
can hear you.
Yeah, thank you. I think this is our last session for the training, and I want to take this opportunity to sincerely thank the facilitators and also the participants who have really managed to be with us for the last 5 days. I know we've been here for 3 hours, so I wouldn't want to take long. So I would like us to request that we fill a survey, a post-training survey that will help us to be able to improve the future survey, future training, and also if at all there's need for us to be able to design a new training. Otherwise, I'm sharing the link. Kindly take some time to fill that form for us. Otherwise, thank you.